Now we're in the signal communication portion of our technical report. This is a very important section. It gives the technician or the engineer an idea of how the components are communicating with your system. In this example, I will start off directly by drawing pictures, and hopefully you can translate these visual pictures into words to put in your report. Okay. As we said before, we have a component called a temperature sensor. I will just use temperature sensor as my example. And that temperature sensor has to communicate with my microcontroller. And we usually indicate that by drawing a line from one block to another block. Now, over time, this temperature sensor is designed to output some type of voltage. The first thing that we have to know is what is the level of the voltage. The second thing we have to know is whether this voltage is analog or digital. Now, our temperature sensor is outputting 10 millivolts for every degree Celsius. I indicated that in the general section, which means that if the temperature was 25 degrees, then it will output 250 millivolts at 25 degrees. Now, sometimes the temperature may come down, which means the voltage will come down, and the temperature may go up, and the voltage will go up. Now, my system is dealing with temperature in a home. So I can expect voltages or temperatures between perhaps 20 degrees and perhaps at maximum 30 degrees. So my system is controlling temperatures between 20 and 30. Using this information, I can calculate the range of voltage that is going to be outputted, the voltage level output of my temperature sensor. So we're talking about 200 millivolts after I do the calculation to 300 millivolts. So we've answered the first question about voltage level. And since temperature is something that just varies, it doesn't jump from one temperature to another, we can conclude that this is an analog. So our temperature, this is temperature, sorry, and this is voltage. We can make a graph and say that between 20 and 30, we will get 200 millivolts and 300 millivolts. So we have some information now. You should write this in your report. Now that we know that this is an analog output and the range, we understand how the temperature sensor works. There's other information, but we'll leave that until later. Now, the microcontroller is a digital machine, so we know immediately that there's an incompatibility between the temperature sensor and the microcontroller, because the microcontroller operates according to a range of voltages that it considers as being a 0 and a range of voltages that it considers as a 1. That's all the microcontroller understands. If you look at the data sheet for our microcontroller, generally it's between 0 and 1 volt and between 2 and 5 volts. Which means that if we try to connect our temperature sensor directly to our microcontroller, it will only read the voltage as being 0 because it never goes above 1 volt. Of course, this is not what we want. We want to be able to know all the voltages between 200 and 300 millivolts, which means we have to add another component between the temperature sensor and the microcontroller. We probably have to add something called an analog to digital converter between the two. My system is using an 8-bit analog to digital converter, which means that if I use 8 bits, I can represent between 0 and 255. So I have another scale that I draw with relation to the temperature sensor. It says as the temperature sensor goes between 0 and 5 volts, I go between 0 and 255, which can be read by the microcontroller. But it appears that the temperature sensor is only using a small fraction of the whole 5 volts. You may decide that this is enough for your design, or you may have to add an amplifier so that you can get a larger range. For example, if I use an amplifier between the temperature sensor and the analog to digital converter, and it has a gain of 10, that means my range of voltage will be between 2 volts and 3 volts, which gives me a more comfortable range. At least I have a 1 volt difference, which is 1/5 of the distance. And that gives me a better resolution for my temperature. This is part of your understanding of the signal conditioning or communication between the temperature sensor and the microcontroller. So we can conclude that the temperature sensor outputs an analog voltage, and then after that we use an amplifier with a gain of 10, still creating an analog voltage but at a greater resolution, and then the analog to digital converter changes those values between 2 and 3 into a binary number, which means the microcontroller will read a parallel code. However, the analog to digital converter that we're using outputs the information in a serial before it's saved by the microcontroller as a parallel code. So we have a lot of communication going on between the temperature sensor and the microcontroller. So in the end, you need to build some type of signal function, whether you choose a truth table, a timing diagram, or a function graph, something that explains how values from the temperature sensor are read by the microcontroller. And you must do this for all of the sensors in your process, as well as all of the sensors, all of the loads connected to your processor. This is what I mean by signal communication. and you can summarize this. But before you can summarize the details, you must understand the details in order to write a proper summary of the signal communication between all of your elements and components in your process. That concludes my summary on signal communications.